ASAP is a research institute at the University of Alaska Fairbanks. We focus on applied research. It means like most of our projects have a direct community connection, and we're really working on creating energy solutions for the state. So the goal of this project was to explore and quantify scenarios that aim towards 100% Railbelt decarbonization in 2050. So two things to note here. We are only looking at 2050, and we are only looking at the electric grid. We're not looking at other sectors in energy, such as transportation and heating. However, we do look at the increase in electric load due to electrification in those sectors. But we're not looking at decarbonization of those sectors. In particular, we're trying to create economic and reliability implications of these decarbonization scenarios. And on the way to these goals, to create information that's useful to the Alaska public and stakeholders, particularly for the Railbelt, such as Railbelt utilities. And unique to this project, in comparison to other projects, we are a university, and one of the goals has been to build in-state capacity and using these tools and analysis. And this also involves training students and interns. And we've trained over half a dozen interns and students over the past 2 years. And for those not familiar, the image on the left is a picture of the Railbelt. So the Railbelt is Alaska's largest transmission grid. It runs from Homer up to Anchorage and up to Fairbanks, and has 4 major electric co-ops and a municipal electric and sewer. So this has been a large undertaking, and we have many people that have contributed to this project. We have the core ASAP team that's worked on this that are here today, and there's many others. I think it's like 15 to 20 plus people at ASAP that have touched this project in some way or the other. In addition, we've worked with 3 other organizations. We have Information Insights here today, working with us on public engagement, the Alaska Microgrid Group, and Telos Energy. And then I'm going to pass it off to Matt, if you want to give a briefer on Telos. Or Derek.
Sure. So Telos Energy, we're a small consulting engineering analytics firm, really focusing around renewable integration. So I think we've done similar renewable integration decarbonization studies really across the country, working with developers, utilities, system operators, and researchers like Alaska ASAP. So really excited to be here. Yeah, that's good.
Thank you. One second. Yeah. Thank you. So in addition to the people that have been working on this project, we are very fortunate to have a technical advisory group. So we've had engineers and managers, staff from each of the 4 electric co-ops, Golden Valley, Chugach, Manuska, Homer, and also from the Alaska Energy Authority and the Railbelt Regional Corporation. We've been meeting with this group of people approximately every other week for an hour for almost 2 years. It's been a tremendous effort, and we're very grateful for all their involvement. They've provided us with data and have reviewed our process and results throughout the project with the main goal to make our results as accurate as possible. And we'd like to acknowledge our funding for this project came from the Office of Naval Research and the State of Alaska Economic Development Capital Funding. So over the course of 2 years, as we work towards the economic and reliability implications, to get there, there's 6 main project components. And so I'm going to give a brief overview, and then we're going to be presenting on the results associated with each of these components more in depth. So we began with scenario development. This is really deciding how many scenarios do we want to have and what is involved in those scenarios, which technologies, which load. And so we developed a first round of scenarios in 2022. And then in the fall of 2022, we had a stakeholder survey. And based on the feedback that we got from that survey, we modified our scenarios based on that. And we'll review the scenarios in a moment. So with the scenarios that we decided to move forward with, we determined a load forecast. So what this is doing is determining what the load is going to be for every hour of the day for the year of 2050. So that's baseline normal economic growth and load. And that also included load growth from electrification impacts. This is particularly heat pumps and electric vehicles. Next, moving to resource selection and sizing. This is determining where are there good resources, such as wind, solar, and tidal. What are the availability of these resources at different locations, and then determining which locations we want to use. And then finally, using all that resource availability information to size, how big do we want these generators to be at these locations? So then with this hourly resource and load data, we move on to generation analysis using a industry standard tool called Plexos, which does production cost modeling. And what this does is create an economic hourly dispatch, which decides which generators are going to be running or operating at which hour into what capacity. And this is all towards creating the most cost optimal dispatch. With this information, so we have the hourly dispatch of each generator for the year. We move into transmission analysis, and here we're really trying to identify what the stability is in terms of frequency and voltage. And instead of doing every single hour out of the year, because this type of analysis is more in depth in both time for computational power and like analysis. So only a subset of hours are actually selected out of the year, which are determined to be the most stability critical to be modeled in transmission analysis. And that's where we answer our questions on, is the system stable? And if it is not, what mitigations do we need to do to make it so? And last but not least, we have economic analysis. So it's really just getting to how much does this cost? So this involves the capital investments, also variable O&M and many other items to get down to what is this change in the cost of service? So we're going to get into some of the details. And so these are our scenarios. So we have 4 scenarios. We have a business as usual. And this is really just a continuation of current practices, essentially. We're only doing projected residential solar growth, and we're only doing announced generation additions and retirements. This is really a reference point to all our other low carbon scenarios. We had 3 low carbon scenarios, each with the major technologies involved in the name. So wind, solar, hydro, wind, solar, tidal, wind, solar, nuclear. And the hydro, tidal, in addition to these technologies, energy storage, battery energy storage was involved in each of these scenarios. And in particular, the hydro, tidal, and nuclear were to represent large investments in these technologies. They are not necessarily the most economical investment, but we really wanted to illustrate what the Railbelt would look like if these technologies were included. And the load that was used for each of these scenarios is the same, including the business as usual. So when we look at the results, we're comparing scenarios that are really like apples to apples in terms of the system. So in September of last year, we did do a presentation on the load forecast. So I encourage anyone who's interested more in the load forecast to revert to that presentation. And there's also a paper. These are available on the ACEP website. This is the resulting monthly demand for the 2050 scenarios in comparison to what was the load in 2021. So as you can see, this is primarily due to electrification of the addition of heat pumps and electric vehicles, that the load in our scenarios in 2050 is approximately double that of 2021. All right, pass on to Jeremy.
Thank you. Got it. Oh. Yeah, so for the resource selection and sizing, as Felicia said, the goal was to identify projects that could be developed for each type of resource. And then in the sizing, we would figure out what we want to include in each scenario and how big to build it. So for the projects that we included, they included existing projects of what's currently on the system, projects that are being developed or being considered, have been proposed, and then projects that we just made up in order to kind of fill out a nice diverse portfolio. So for hydro, the projects, these are all existing projects or projects that have been proposed. For wind and solar, we have existing projects, we have proposed projects, and then we made up a few projects just to kind of round out and have a nice resource mix in each region on the Railbelt. Residential solars in the part of the load forecast, we also forecast what a residential growth in residential solar could look like. And so each region on the Railbelt, the Railbelt can kind of be divided into north, central, south. And so each region has a certain amount of residential solar that we included as well. Tidal, so Cook Inlet Tidal is something that's being looked into, and it's something that is being under consideration. So we have that, and then for nuclear, we selected locations on the transmission system that would be ideal to site nuclear. So we identified projects to include in different scenarios, and then we tried to size the different projects for each scenario. So based on the input assumptions and the goal for the different scenarios, we tried to size all the different projects that went into those scenarios. And as we said earlier, so some of the projects, some of the sizing was predetermined. So the hydro, tidal, and transmission, that was determined when we developed the scenarios. We said, okay, so Sinawatana gets built in the large hydro project. And so that we didn't have to, so the sizing and the projects for hydro, tidal, and transmission in terms of what gets built and how big was all determined in the development of the scenarios based on, previous studies that have been done and what's been proposed and what we wanted to demonstrate in the different scenarios. The remaining wind, solar, battery, nuclear, and fossil fuel, those remained to be sized. In fact, that's what we did in this part of the study, where we try to use cost. We try to optimize the remaining components on the grid to come up with a least cost system. And the way we did that is the diagram on the right here kind of shows roughly what it is, but in general, we're just iterating. So we come up with a system portfolio for a scenario. We run a simplified 1-year simulation. We calculate the annual cost resulting from that 1 year based on the capital costs as well as the operating and fuel costs. And then basically we have an optimization algorithm that will continue to iterate, will continue to build new system portfolios until it iterates and converges on a lowest cost system. And so we do that for each scenario based on all of our input assumptions. And there's a lot of input assumptions that go into something when you're projecting out to 2050. And so one important thing to note here is that these are only partial optimizations. So because we built the scenarios, we built the scenarios with some assumptions about what gets built and what each scenario is going to look like. These are not meant to be interpreted as the most optimal scenarios, the most optimal way, the scenarios for 2050, but these are more illustrative scenarios about different potential resources mixes that have been proposed and that are being looked into. So some of the results. So the bar chart on the right here shows the installed capacity by type, generation resource type, for the different scenarios. So the different bar colors, blue is wind, solar, hydro, orange, wind, solar, tidal, gray is wind, solar, nuclear scenarios. And then we have the different types, wind, solar, etc., for different bar clusters of bars. And the height of the bars is the size in megawatts, the combined size of the total installed capacity on the system. So there's two main points from the results of the sizing part of the study. And the first is that wind and solar, with the cost projections that we use, and including in the sensitivity analysis, where we looked into different cost projections, but in general, wind and solar pretty consistently always ended up being the cheapest sources of energy, with the caveat that the amount of load that you could serve with wind and solar is limited, based on economically limited, based on the cost of curtailment. because once you start installing more and more, you're going to have to start curtailing more and more at the high, even during the moments of high net generation. And so essentially economically, the amount of wind and solar that gets built on the system is limited based on the cost of curtailment. And it's important to note that there are additional costs associated with wind and solar that were not included at this point, which are stability costs. And these were determined, Felicia will talk about them a little later in the slide, but these are in the transmission analysis part, we go into the stability costs of wind and solar. But so wind and solar, they're great. They're cheap sources of power. You can't serve the amount of load that you can serve them economically is limited. So that leads to the second point is we need firm sources of power. Firm just means you can rely on it to provide power whenever it's needed. And so depending on the scenario, some mix of hydro, nuclear, fossil fuel, and to a limited degree, batteries provided this firm source of power. And I'll highlight, so the nuclear scenario is a little bit unique. So nuclear was the one firm source of power, excluding batteries. The one firm low carbon source of power that was built, that we sized using costs. So it was not, we didn't determine the size of nuclear in the scenario development. We used cost to try to optimize the size of nuclear and all that. So, and basically with the cost projections that we had, it was not competitive with imported LNG as a part of the entire system. And so what we did for the nuclear, wind, solar, nuclear scenario is that we said, okay, we're going to assume there's no LNG imports in this scenario, which made nuclear cost competitive to be a major part of the system. And so, yeah, so the goal of that was to have a scenario where nuclear was a major component. And then the other benefit is that, we also had a scenario that demonstrated a future without LNG imports. And there may be other benefits other than just pure cost on not relying on LNG imports. So I think this is something that is also interesting to look into. So that's something that's unique about the nuclear scenario. And that ties into the final point is that, cost projections are extremely uncertain when we're looking this far out. And so we did run sensitivity analysis, they're in the report. What the sizing that we have here, this is based on, one set of assumptions, cost projections that was used to size this. And basically cost projections, this is especially true for more nascent technologies like nuclear and tidal. So all that to say, take it all, the sizings, the optimization, like don't take this with a grain of salt. This is what we came up with. It's not the Bible in terms of this is what you should do, but this is what we ran with to do the rest of the analysis and come up with our other results as illustrative scenarios. And here we get to generation.
All right, thank you, Jeremy. So the next step in the project is, it's great to look at the cost of the different resources and some different configurations of that. But really the next step we wanted to look at is this system operable? If we're going to move to a system that has much more wind and solar batteries on it, resources that are not always or uniformly available, we want to make sure that system is operable. And so the next step in the analysis was what we're calling the generation analysis. And the questions we're trying to answer here is really make sure that the system works, not just when we look at a really high level or an annual basis. We want to make sure it works on an hour-to-hour basis, right? When we think of the operators in the control room at the utility and folks running the grid, we want to make sure it meets the reliability needs on the system, all of the operating constraints on the system. And so that's what we try to do in this step of the simulation, or this step of the study, is to make sure, kind of take that role of the system operator and make sure that they have the tools and the ability to run the system while meeting their reliability needs. So questions we're trying to answer is, how should these different resources be scheduled? How can the grid operator manage the variability? If it's windy one hour and not the next, how can they manage around that variability? Batteries, a very new technology in many parts of the world, and how should those actually be controlled? How should you schedule the batteries? When should you charge? When should you discharge? And how does transmission, how does power move across the network differently with a different resource mix? So to do this, we go through a series of simulations called production cost simulations. The inputs, what we put into that is hourly load profiles. So the load on the system, how much consumers use electricity, will fluctuate hour by hour, season by season. So that goes in. The wind and solar profiles, of course, it's changing every hour of the year. So that's an input. When we think about hydro, some months have more hydro available than others. There's a wet season, a dry season. We have our coal, our existing thermal resources, all the gas, the coal, the oil on the system. All of those plants are a little bit different. They have operating characteristics, limitations. They have different fuel prices, different heat rates going into them. So we bring in those constraints, and each of the 3 Railbelt utilities were great about sharing data on how their systems operate. And so we try to reflect those realities. Operating reserve requirements. So basically, this is what happens if there's an emergency on the grid. We need to make sure at any given time on the system, the power grid is able to respond to those emergencies. So we put that in, and then the transmission system. So those are all the inputs. We put that into a tool. We use a tool called Plexos. This is an industry recognized tool used by a lot of utilities and system operators to plan out the system. And it goes through and says for every hour of the year across all 8,760 hours, what's the least cost way I can schedule all my resources while serving load and meeting all the reliability obligations. And coming out of that, we're using this tool for a few different reasons. The first is to get all that information about plant operations. When do plants start? How often do they stop? What is the total fuel consumption? What does that cost? We can then use that, and it goes into some of the downstream applications. So Matt's going to talk about how we use that to come up with some of the stability analysis. Steve's going to say how that flows into some of the economic analysis. And so here's a snapshot. Jeremy talked about the composition, the capacity of the different resources going to each scenario. What I'm showing here is the total generation across the entire year across our 4 different portfolios. So on the left, you can see business as usual, a segmented bar chart of the total generation by each fuel type. The gray is the existing gas and fossil resources, and you see a little bit of hydro and wind at the top. And you go through the other 3 scenarios, and you can see now the zero emission resources growing quite a bit, becoming the primary source of energy across all of the portfolios we looked at there. You can see in green and yellow, those are variable renewables, wind and solar. Blue is hydro, so you can see the Susitna-Waitena project. Pink is the nuclear, and I guess the lighter pink is the tidal. But we're not really concerned in this segment about what the annual generation is. We want to see, again, that hour-to-hour generation. And so this is stepping through kind of a typical winter day. You can see, yeah, so this top line here, that's the load across the day. You see early in the morning, the load ramps up, settles down in the middle of the day, and then ramps up again in the evening. And so it follows that pattern kind of day in, day out. And you can see kind of in this business as usual scenario, the gas is following a very predictable pattern, following that load pattern. And then at the top, the red, these are what's called a peaking resource, a little bit more expensive to run, but they're very quick to start and stop. And then the hydro kind of smoothing out the peaks at the top. When we step forward to some of these other portfolios, you start to see that dispatch change quite a bit. The big thing is the fossil units, the gas units, because they're more expensive to run on an hour-by-hour basis, higher fuel costs, they're dispatched down to a lower loading level. The renewables are really displacing that. You're also seeing a lot of movement. So the chart on the left, very smooth, kind of predictable across the day. You're starting to see that variability kick up and things are moving around quite a bit. And so that's what we're trying to evaluate here, is making sure that system is still operable. With that, you can also see the battery storage charging during the high renewable periods. And then in this evening peak, you're starting to see it discharge. So again, that's what we're trying to do, is step through these scenarios, make sure the system is operable on an hour-by-hour basis. And so that's what it looks like without the hydro. And then again, with the nuclear, running base load there at the bottom, and then everything moving around that. And so we're going through that process, not just for one day, but we also use this to select specific hour. And I'll pass this over soon to Matt, and he'll talk about how we look at some of these individual hours in a lot more detail for the transmission stability. So Matt's going to talk about these dispatch conditions that get evaluated more in stability analysis. And so I want to show how we kind of zoom in on particular periods, and we're going to look at those in more detail. Well, again, we're not just doing this for a single day, we're doing this for every day of the year. And so this is a weekly snapshot of very similar, and you can see again that fluctuations, and what we're trying to show here is how you manage that variability. And you can see the different resources moving up and down. You can see there's periods here in the middle. It's a low renewable period, and you're starting to see some of the other fossil units fill in around that. And then in the hydro, certainly the hydro is providing some of that flexibility on the system. So we're walking through this day after day, week after week across the year. What that gives us is this timing of wind and solar generation is going to vary considerably across the year. So when we talk about some of these portfolios being 50% wind and solar, well, it's not 50% wind and solar all year. It's going to operate across an entire range. And so what you're seeing here is it's called the duration curve. We just sort all 87, 60 hours of the year. We sort them from highest to lowest. And you can see down at the right, there's some hours of the year where the wind and solar is doing absolutely nothing. On the other end of the spectrum, there's times where the wind and solar is over 100% of load. You say, well, how does that happen? And the battery storage. So that's periods when the batteries are being charged. And so again, as a segue into the stability analysis, this far left quadrant, that's a period where additional analysis is required. That's really pushing the envelope of where power systems are operating today. Globally is kind of above that 70, 80% instantaneous penetration. That's really requires more detailed analysis around stability. The last thing we look at is not just the timing of this generation that's changing considerably in these different futures, but also the location. So today, again, the system's made up of 4 Railbelt utilities across these 3 areas. What we're calling the north with Golden Valley, the central here, and then the Kenai Peninsula. And there's interties between those 3 regions. And so this is looking at the flows, the transmission that flows between the northern and central regions of the system across the Alaska intertie. And you can see here on this, again, that duration curve that's sorting from lowest to highest. The gray is the BAU, so relatively flat. Not much utilization of the transmission system, certainly there when the system needs to import or export between the regions. But what you see in each of the 3 high renewable scenarios or high decarbonization scenarios, a lot more flows in both directions. So now the grid is being utilized much more. The transmission system's being utilized much more, moving power from north to central, central to north. And certainly in the case with the Tidal down on the Kenai Peninsula, that's pushing much more central to northern relative to north to central. And again, the other main intertie going from the Kenai up to central, this is showing again, same thing, the utilization across, in this case, almost always from the Kenai Peninsula up to the central region, as that renewable energy is flowing up to the major load center in Anchorage. So again, timing of generation is stuff we have to really think about, also the location. And both of those are going to segue well into the next step, which is the transmission analysis.
All right, thanks for the setup, Derek. So to begin the transmission analysis discussion, I'll talk a little bit about what is it? What are we analyzing to make sure that these scenarios can actually work and can be stable, and that if something happens on the grid that is unexpected, can the system recover from that successfully the way we would expect it to and keep on running and keep the lights on? There are 2 big aspects of how we talk about continuing to operate. One is in a steady state analysis, and the other is in a is called a dynamics analysis. And steady state, we're looking at, can the grid sustain the operations that it's under in all credible grid conditions? And so that means when we talk about it in power systems engineering, it's your N-1 or your loss of any element with no forewarning that it's going to happen. If you lose any element on the system, can you keep going? And as part of that, There's the thermal analysis, which is looking for basically the power carrying capacity of the lines. And then there's the voltage analysis or voltage violations that you could have to ensure that you have enough support of the voltage to keep all of the voltages across the system in their normal operating conditions. On the dynamic side, the dynamic analysis is really looking at, can the grid recover from the sudden shock? And so this is a time series analysis where an event happens and you're looking at the milliseconds and seconds that follow that event, all of the things that move on the system that get the system back into a normal, stable, and steady state operating point. When we talk about the dynamics analysis, there's two key factors on the grid that we're monitoring. It's the frequency of the grid. In the US and a lot of other places, it's 60 hertz here, and then the voltage stability. And so when we're looking at that, we want to see when a disturbance happens, the grid frequency can move away from 60 hertz briefly and to some degree, to some magnitude, but it has to get back pretty close to that value pretty quickly. Similarly, on voltage, voltage has, say, what we talk about in the per unit system, like 100% voltage being a normal operating level. It can deviate from that actually dramatically, but briefly, and it has to be able to come back and get back to that in order to continue running. These analyses are performed as snapshots in time, right? So as Derek mentioned, we really care about how the grid operates over the course of the year, but we can't study a year's worth of operations, thank you, a year's worth of operations at this level of detail. And so what we do is we choose specific points in time that are particularly challenging to understand, okay, if it can survive that, it can survive all of the others. So the challenges that we're talking about in steady state have been touched on before. There's a lot of new resources, retirements, and they're in different locations, which means the transmission system is delivering from source to loads in different ways. It's being utilized. Different lines are carrying the power in different paths than what we may be accustomed to in other scenarios or how it works today. Dynamics, what we're considering, the challenges are a sudden loss of a power plant. That sudden loss of generation, if that happens, has to be made up for very quickly in order for the system to keep on running. Also, a loss of a tie line, and in particular, the major tie lines being the Alaska tie line between central and north, and the Kenai tie line between the south and central region. When that happens, you're necessarily separating the system. The Railbelt comes apart into two pieces, and then are those two pieces independently viable? And in order to ensure that, essentially you need a response from all of the collective remaining resources. You need enough response, and you need to deliver that response in time for it to be effective. So when we look at the grid, we've been talking about hydro and fossil and wind and solar. When I look at it, I see these two things. I see synchronous machines, or that technology of how that resource is delivering power to the grid. And I see inverter-based resources, which is the other major way that power is delivered to the grid. Synchronous machinery has dominated all of the conventional technology, fossil, nuclear, hydro. Inverter-based resources are how the wind, the solar, and the battery and the tidal resources interface with the grid. And those synchronous machines, those large rotating masses of steel and copper, the behavior and the response that you get from those is determined basically by their physical geometries. So it's predetermined in a sense up front in the design of that equipment. You put it on, you know what it's going to do in these disturbances, or you can represent it very well. With inverter-based resource technologies, these are essentially software defined. They're like computers that are controlling what is happening to the grid in real time, moment to moment. And so what they do depends on that software that is running. And so that's great in the sense that there's a tremendous amount of flexibility to respond and provide really good stabilizing behavior. There's also the corollary is there's the power that has, and there's the ability to get it wrong and to provide the wrong behaviors and to do the wrong thing at the wrong time if it's not done properly. And so that is really the focus of what we're looking at in this analysis, and what types of characteristics do we need to see from this equipment. To do this, we looked at a couple different hours, just a few different snapshots in time of particularly challenging periods of grid operations from the analysis that Derek described in the generation analysis. And the selection for that was based on two things. One, when are the periods of time when the generation is largely coming from those inverter-based resources? So when you have that, you're necessarily backing down and basically turning offline all of your conventional equipment that we've typically relied on to provide these stabilizing characteristics and services to the grid. Second, at what points in time do you have the highest loading on the tie lines between them? And the reason we look at this is because if you have a lot of transfer on the ties and you suddenly lose the tie, you're interrupting a lot of power flow, and it's a larger shock to the system. And so we looked at the combination of these to really see what are the most stressed conditions that the grid in these future scenarios will have, and can they recover? Briefly, on the steady state analysis, we identified both thermal and voltage violations. So for thermal violations, there were some lines overloaded, again, because of the different flow patterns on the grid. And we proposed there's a combination of upgrading the system through a combination of new lines, as well as reconductoring, or basically leaving the poles in place and replacing the wires to a larger wire size, essentially to carry more power. On the voltage side, for the voltage violations that are identified, what we found was the voltage in many cases, many contingency cases, would drop, indicating a lack of voltage support for that condition. And in part, the voltage was dropping because two things have been assumed. One, the system is now supporting more load. And so there is more, because of the electrification and, for instance, electric vehicles coming online, there's more demand for that power. The transmission system is carrying more power. And when it does that, it increases the demand for supporting the voltage. In order to do that, there's a number of different sequences, some very simple and some more complex and more equipment intensive, for providing additional voltage support to continue operation in those conditions. When we switch over to the dynamics analysis, what we started with, and I'll show an example here, and please call me if I'm going on too long on time. Okay, so far still. You just get the big hook and drag me off. For the dynamics, the initial results, what we started with was we're running these simulations, these computer-based simulation models. And by the way, we're using the same software that the utilities on the Railbelt use, and that's used around the world. And we started with modeling the high hydro scenario, and we looked at the loss of the tie, the Kenai intertie. And what we can see originally is you don't have to be an engineer to look at these graphs and say something doesn't look quite right. They're bouncing around. It's essentially a failure to control frequency and voltage on the grid. And what's happening, the time scale is hard to read, but this is those are 20 milliseconds per division, right? So this is a small fraction of a second on the whole window. It's happening, all this is happening very quickly. And so what we see is, this is with our initial representation of the wind and solar, those inverter-based plants, as they are typically being commissioned today. And just kind of the normal responses that work today with the relatively low penetrations of renewables would give a result where the system in this stressed condition would basically come apart immediately. And so we said, okay, there's clearly a problem here. What are the mitigation approaches that you can take here? And we categorize those in a few. One, there's an operational approach to mitigation, which is meaning you can force on some of the conventional technology, those synchronous machines, to stay on and provide those services. That can work well for small periods of time where you don't have a lot of hours of operation that are doing that. But if you're going to operate for a third, a half, or a majority of the year with high levels of renewables, you would prefer not to. It would be uneconomic to force those generally fossil-fired plants online and curtail the renewables. And so that's mitigation we were not pursuing here, although it is a possible one, so we included it here. The other option is the capital investment mitigation. Without going into too much detail here, you could utilize synchronous condensers or convert existing plants to synchronous condensers. And a synchronous condenser is essentially a part of the rotating machine, the generator part of a power plant without the turbine part of it. And so it doesn't burn fuel, it doesn't produce energy for the grid, but it does have the generator retained as connected to the grid and providing services for it that can support voltage and help control frequency. The other mitigations are the software mitigations, where we'll focus on in particular. This is the tuning of that software that I was talking about that drives the behavior of those inverter-based resources. And so there's the ability to tune the conventional stuff to make it more aggressive and more responsive and faster. And there is a limit to that. And then there's another control paradigm, which I'm going to refer to as grid forming inverters. This is a new emerging technology in the industry that basically adopts or takes some of the best of both worlds from the two different technologies. And I'll get into that in a little bit more. What I want to show briefly here is an example of an output of some of the time series simulations that we've done for applying these different mitigations. On the table at the top, you can see we look at what I'm calling the GFL only, which is grid following inverters only. That's kind of the conventional inverter technology. You see that the system collapses for this particular case. This time we're using the example of the loss of the Alaska intertie. If you add the synchronous condenser technology that I was talking about, you see that the system actually becomes stable. So in yellow, it doesn't come apart, but it requires a lot of this type of technology, which either would have to be converted or produced or procured for new units. If you add some of the synchronous, if you also tune up the the conventional inverter technology, make it more responsive, you don't need as many of those synchronous condensers online to keep the system stable. And then when you go to the grid forming inverter technology, this new control paradigm, you see that you can keep it stable. And in many cases, there's no need for synchronous condensers at all. So overall, the system has much better stabilizing characteristics. So if you contrast this case with the loss of the tie, you see that the two systems in blue and red, the north and the blue, the frequency goes very high, and then actually it ultimately collapses. And same with voltage is ultimately uncontrolled. In contrast with the use of the grid forming technology, if you have enough of that on, you see the responses are pretty well damped. And after about a second, they recover to a new steady state and continue. That's what a successful recovery looks like to us. And so the grid forming inverter technology, this new emerging technology, is an important finding in that it can actually enable stable operations in these scenarios where we're really pushing the system very hard. It looks very different from how the Railbelt is being operated today. And so there's a lot more I'd love to talk about, but I'll keep it very brief here and now. Essentially, what it is doing is you're writing software in a way that you are capturing the desirable and stabilizing behaviors and characteristics from synchronous machinery in the short time frames, and you're also capturing the benefits of the the stabilizing characteristics of conventional inverter technology in the slightly longer timeframes, where each of them have a strength. And if you can pull the best of both worlds and wrap them into kind of a new product, that's what we're calling grid forming inverter technology. And so we've gotten a lot of questions. Okay, this is great. You know, you've got this magic thing here. Like, how is it being utilized? Is there any experience? And there is. It's growing. There are a number of projects that are actual real world projects made by real equipment manufacturers that have been installed now for about in the past 6 or so years. This list is incomplete. It's growing all of the time. This technology, though new, and while there's not a large installed fleet of it, it is operating on real systems and keeping the lights on for real paying customers. And we're gaining experience with it rapidly. I think you know, we've done a lot of work vetting this. I'll admit I was personally very skeptical of what this technology could do until we got a lot more experience working with it from different manufacturers, testing it to see what it could actually do. And so with that, I made this note, you know, the software that we're using is a robust and commercial software that is used for this types of analysis. That said, it's not trivial to use. There are literally thousands of inputs to this. Conditioning it, understanding the results it takes a lot of judgment and time and specialized skill. And the ACEP team has done a great job of that, working through that. So as we get into the economics phase, I'll pass it off to Steve, but just wanted to share a little bit about the process that we've gone through in sharing these results. Jeremy laid it out in the beginning in terms of starting with the resource sizing, going to the generation analysis, and then the transmission analysis. And that is what is highlighted in each of these. In the first bit, we have resource sizing, and each bar chart is speaking to the different resource mixes. And so if you kind of, you know, this is a bit of a heavy chart, a hard figure to read, but as you see, for these first three, you can see the bar charts are evolving a little bit, and they're growing a little bit taller, and we're adding some new colors. And what it's saying is we started with an initial resource sizing, and we went with that, and we ran the generation analysis. We found some operational constraints in terms of how the system is working. And so we would add, for instance, battery energy storage to help smooth some of the variability. And then we would go to the transmission analysis, and we would find, okay, that didn't quite work. We needed some more stability on the system. And so we would add, in many cases, it is kind of a basket of stabilizing technologies, including battery energy storage. And so we would add a little bit more. And that held true for all of these different scenarios that we looked at, the nuclear, the hydro, and the tidal. And this process is ideally it's iterative, right? You get to find, okay, I needed to add some more, I needed to add some more, I needed to add some more. And then you kind of turn around and say, okay, well, if we changed some assumptions that we had made in the earlier part of the process, we could go back and get a more optimum answer. Where this study has gotten us today is that we've made that one first pass through. We've gotten to show a viable system, but it's not necessarily economically optimized. And having more time, you could certainly go back through and keep the system working and reliable, but make some adjustments. For instance, connect a project in this location and not in that location, or change some of the tuning of some of the other support and initial assumptions that were made to ultimately lower the cost. So let me hand it off to Steve to talk more about the costs.
Thanks, Matt. Which is the flashlight? The middle? Top. Okay. So now that we've come all this way, and for us, it's been a 2-year journey. It's really fair to say that what I'm going to talk about really is just arithmetic at this point. And the real economic analysis, which has been limited by design, has already been embedded somewhat in Jeremy's work. He did a lot of work writing software to try to come up with, let's call them economically sensible resource portfolios. Perhaps not optimal, but way better than if we had just thrown darts. And similarly, the work that we've labeled generation analysis with the Plexos tool, that's actually a highly sophisticated optimizing algorithm that's trying to find out the least cost way of running the system that you give it. So really, there has been a lot of economic analysis and attempts to optimize to some degree the system along the way. And what I'm going to just do as a wrap up is really arithmetic. It could be called accounting, but we're just going to add up the costs that have been accumulating with all these resources. So the first slide, and just maybe we should state for the record that the slide deck will be available. So these are hard to read for me, so I'm imagining you're going to need to go look. But this slide is intended to show how much capital investment would be required. And it ranges from about $2.2 billion under business as usual, where we would need to add some fossil generation, that's dark blue, to up to 12 billion if we went forward with a project like Susitna-Watana, which is a very capital intensive, very costly project. And that is the bulk of the, hope I don't blow this up. Yes, that's Susitna-Watana, huge chunk of capital investment. And the well, to me, the neat thing about this graph is the difference is that we've unbundled the orange and the yellow. They are both basically batteries and some of this other stability equipment that Matt was referring to. The orange bars are the batteries that we needed to have a viable economic dispatch. They were used basically for storage, smoothing the wind, and some operating reserves. The yellow bars is the stuff that Felicia and her team had to add to the system to make it stable and able to recover from these disturbances. And so the yellow bar is mostly batteries the way we spec'd it out. It's got some of these synchronous condensers in there. And Matt's last comment is very apropos. We didn't really have a chance to go back and say, could you do it cheaper? We basically threw a bunch of batteries at the problem to demonstrate that you can make the system stable. And the simplest analytically way to do it is to add a bunch of batteries with this grid forming inverter technology. But the point, I guess, one point you could take away from this picture is that the additional yellow chunk of stuff is not an overwhelming addition, which I think was, I don't know if you guys would agree, was somewhat of an open question. Felicia is the first person to try this for the Railbelt. And she deserves many gold stars and medals for doing it. And she had a team, some of whom are here, working with her, and they did amazing stuff. So the capital investment is shown here, and it is dominated by these anchor projects, whether it's big hydro, a big tidal installation, or two medium-sized nuclear plants. And some of you may be wondering, is this pre or post investment tax credit under the Inflation Reduction Act? And the answer is this is after application of a 30% ITC on all these capital investments. And 30 is the number that we're using as our basic assumption about what you could get from the IRA. So that's the capital investment post ITC. It's a lot of money, but it's my last comment on this one. And I should have a slide to show it. Maybe my next slide will show it. It might seem overwhelming that you could put $12 billion into redoing the Railbelt electric grid. But here's the thing, we're currently spending, well, we're not currently spending. Under the BAU, you will see in 2 slides, we would be spending about $750 million per year on fuel. So maybe I should have said $750 million a year on fuel is what the BAU gives us. And that provides a little bit of perspective on what 12 billion would entail. So I don't know if this slide is worth going into, but you can go and sort of double check what we tallied up. When we tallied up, we tried to tally up what would the cost of service be, and I deliberately restricted that cost to be the cost of basically the cost of generation and transmission, getting the power produced, getting it shipped to the distribution system. And we didn't get into the weeds of whether how the distribution system might change. It might cost less to run the distribution system if you double the load and you can more effectively use your distribution assets. We didn't go there. So this is what we call the G&T, or generation and transmission cost of service, that we're going to look at right now. And here's the base case G&T cost of service. Under the BAU, it is dominated by fuel, dark blue. And it's about 84 bucks per megawatt hour, which is 8.4 cents per kilowatt hour for fuel. And it's the lion's share of this G&T cost of service. The lighter pink is fixed O&M, and then capital cost for some of these new fossil units and some new transmission is the top, the orange. And then when you go to the low carbon scenarios, they all feature this fundamental shift of paying for fuel over to paying off capital investment. And then another thing that I think is noteworthy to me is that these zero fuel resources, some of them have pretty stiff annual maintenance requirements. And I think we were pretty conservative about not being too optimistic about how those might go. In other words, we had robust Alaska cost multipliers on this fixed annual O&M stuff. And to me, it was a little bit of a surprise that it would be such a major cost component, but there it is. And so the other thing that was a surprise to me is that these costs are all really quite similar. I had no idea it was going to come out this way, and I can say with a straight face, we did not go back and tweak any of the inputs to get to this relatively level cost result. It's just what came out of, like I said, essentially arithmetic at this point, adding up all these costs that the other exercises had said we were going to need. So the last thing to show you here is a bunch of sensitivity cases that we ran. There's 5 of them. Go through them pretty quickly. Just to kind of explore what happens if you vary some of the things that we know are highly uncertain. So here we go. 5 comparisons. The first one is to say, well, what happens if fuel costs were 20% higher? The baseline assumption, one slide back, was $14 per million BTU gas. That's the key critical assumptions. So what if gas and oil and coal for that matter, but especially what if gas were 1680 instead of 14? That's 20% higher. Well, then you see that the capital intensive fuel light renewables actually come out cheaper than the BAU. Whereas in the base case, they're, a little bit more expensive. So that's fuel plus 20% sensitivity. On the other hand, what if interest rates were 20% higher? Well, it's kind of predictable there that then the capital intensive renewables are gonna do worse. And they're gonna look now significantly more expensive than the BAU, the fuel intensive BAU. Then we said, well, what if the interest rate is high and we underestimate the capital costs of these big projects? Well, then things look even, you can see it, things look even worse for the renewables relative to a BAU setup. Conversely, what if we are too pessimistic about the cost of some of these big projects? Maybe technological progress will give us much lower cost than we have today. We know that has been the pattern for some wind and solar resources, but we did not project continuing technological learning curve advances beyond 2030 in our costing of wind and solar. So if you apply a 20% drop in the big projects and you consider maybe a lower interest rate, once again, the renewables look better, but they still all kind of look, relatively similar. Okay, I might have frozen. Maybe I'm not pointing in the right place. I'd like to advance my slide. Maybe you can just do it. Oh. Not eyeball. Okay, so we have advanced from S4 to S5. This is the last sensitivity case. And this is one where we make the assumption that all of these projects could get not a 30% ITC, but a 50% ITC by taking advantage of the so-called bonus credits for domestic content and being situated in what the Inflation Reduction Act calls an energy community. So with a 50% ITC, then once again, the capital intensive portfolios look in some cases significantly less expensive than the base. So those are 5 sensitivity cases. Come on. Oh, good, thank you. And I have a very sort of maybe simple-minded takeaway from all of these sensitivity cases. Obviously, you can't read them on the screen, but you can find them in the report. You can find them on the slide deck for yourself. And the bottom line of the sensitivity cases is that you can, the most favorable case for not low carbon resources is down here, 50% ITC, heavily capital intensive nuclear scenario, 9% below the BAU. Conversely, if things go badly for renewables and capital investment, the highest change you get from sensitivities is to be 25% above the BAU. So it's sort of like a -10 to +20 kind of range that we get out of these sensitivities. But of course, these are just illustrative sensitivity cases that try to sort of just explore the uncertainty. And my simple-minded takeaway from all this is all of these costs, here they are, 4 scenarios, 1 base case, 5 sensitivities, 24 bars. My takeaway is that they are all in the same ballpark. Fenway Park, if you're curious. So again, that's my personal takeaway from this exploration of the costs, given the assumptions that we were able to put into them. And that's all I have to say.
All right. Oh no. So we're wrapping up here. So we've thrown a lot of information and a lot of numbers at you. And what I'd like us to focus on is, instead of the individual numbers that you'll see here, is really the focus on the challenges and the opportunities that we've identified. I think this is where the key takeaways are. So in general, the low carbon scenarios represent a very different operating scheme than what we have today, or in a business as usual scenario where we are largely dependent on synchronous machines. This would be a significant change to the rail belt, and this type of change does not happen overnight. These are incremental changes that will happen over time. We are talking about 2050. The system stability is going to be more difficult to achieve in these low carbon scenarios. Improvements in inverter technology of batteries, such as grid forming inverters, and wind and solar energy are really essential to having a stable railbelt grid in a low carbon scenario. As Steve has mentioned, there's great uncertainty in all of these future costs, 27 years into the future. And from these sensitivities we've identified, the cost of service of the low carbon scenarios differs anywhere from -9 to greater than 25% than the business as usual. We'd also really like to note that the study did not evaluate the cost effectiveness of near-term renewables. We did not look at 5, 10, 15 years into the future. The cumulative cost of achieving these higher and greater levels of renewable penetration are not linear. You know, you kind of have step changes where you need to add, say, more transmission or certain types of equipment as you get to higher and higher levels. And additionally, from now until at least 2030, all low carbon projects qualify for that investment tax credit, which can range from 30 to potentially up to 50%. And so these are some challenges and opportunities. And now let's wrap us up. Jeremy?
Yeah, so just touch on some next steps that we're considering. We have got a great start with this project, and there's a lot of fun opportunities ahead of things that we can look into. But you know, time and resources are limited, and our brains are limited. So we unfortunately need to pick and choose to some degree. And so I just want to highlight a few of the areas that we're thinking about, and later this evening we'll ask for your input on some of them in terms of what you think would be beneficial for us to look into next. So the first one here is focus on finding lower cost scenarios. So, you know, as we saw, you know, the scenarios weren't necessarily lower than our business as usual scenario. They're kind of the same or a little bit higher for the most part. So as we said, these were illustrative scenarios where we've built a lot of things and didn't iterate and didn't necessarily get to a lowest cost system. So that's still out there, still to be found. That is, you know, definitely something that would be interesting to look into what that would look like. We could focus on achieving higher levels of decarbonization. We didn't get to necessarily 100%. There are, you know, different things that you could add to the system. You could, you know, add more low carbon generation or use carbon capture or alternative fuels, or there are other technologies out there to look into. But, you know, should we try to reach higher levels of decarbonization? And something, well, another area that we've had a lot of interest in is how can electrification lower consumer costs and carbon emissions? So kind of draw a little bit of a bigger circle and not just look at the electric system and serving electric load, but also look at the consumer and what is the benefit to the consumer of different scenarios and in terms of especially electrification of their loads and their energy needs. And then looking kind of on the policy side. So yeah, connections between policy and emerging technology on these future scenarios. So, you know, there's a lot of different technologies out there that are, you know, becoming emerging technologies. And there's, you know, the role that policy such as tax credits or mandates that can have big impacts on you know, where a scenario will go and what makes sense, what doesn't make sense in terms of costs or requirements. You know, we can dig deeper into stability issues and solutions with high levels of renewables. So that's kind of, you know, what Matt and Felicia were working on. And there's definitely a lot we can do to kind of dig deeper in there and improve or, you know, optimize more with the rest of the system. And then dig deeper into the impact of natural gas supply pathways on scenario development. And so I think we're probably all familiar with the Cook Inlet gas supply. And so in our scenarios, you know, we just looked at a snapshot in 2050 and we assumed LNG imports was the most likely scenario in that in 2050. But, you know, when looking from here out to 2050, you know, there's a lot of pathways that involve, you know, the economical or low cost gas and Cook Inlet running out and the needing to replace it with something. And so what the contracts with that, the options for contracts and price projections, and then also the physical, you know, what the physical system looks like in terms of the natural gas supply to the system will have big impacts on basically what an optimal pathway to achieving a better energy future would look like. So these are some of the different things that we're considering, and definitely open and we'll love to hear other ideas. But yeah, I think later today we'll have a bit of a poll looking at asking for input on these. So now I think we're opening it up to questions.
Yeah.
All right,
Yeah. Can we get,
So
Josh. Oh wait. Oh yeah. Sorry.
we're going to take questions
Right.
from both the online and here in the audience. I'm going to start with one for Telus, I think. Maybe Derek, you can, are there other places like the Railbelt that are facing similar challenges, and what are they doing to decarbonize?
Sure. Thanks for your question. Yes, I would say this is all of the opportunities, challenges that we've discussed tonight are happening everywhere and happening very quickly everywhere in the world. And a lot of the work we conduct is doing this type of analysis, this type of system planning, really across the country. What makes the Railbelt unique is it is a remote islanded grid. So while it's not an island electrically, the Railbelt is an island. And so there's a lot of really specifics that need to be considered. A lot of the stability challenges are more pronounced when you're on a islanded or a remote grid. The variability is also, you know, more challenging to maintain because you can't lean on a neighbor when the wind drops off or the solar drops off. So that's unique. So a lot of our experience in this type of work is found in other island systems. And so we've done quite a bit of work over the last 10 years in Hawaii, which seems like as far as you can get from the Alaska Railbelt, but electrically speaking, a lot of similarities. And that's a good example to draw on because made up of 5 isolated power grids on each island. They've really, I think when Matt's talked about a lot of the stability challenges, they've gone into the pathway towards grid forming inverters and a lot of solar plus storage resources there. So really leveraging battery storage is that key enabler. They've had quite a bit of renewable growth over the past 10 years, but really what's helped them turn the corner and push to even higher levels has been battery storage. So the grid forming inverters that Matt has talked about have been in use on Kauai for the last few years with their solar and storage installations. And then this last couple of weeks ago, a very large battery storage system one in Oahu. And also with grid forming capabilities. So yes, there's a lot of other regions that are grappling with these same challenges, really pushing the forefront of where the industry can go. And it seems like every year, every month, there's a new record being broken on instantaneous penetration, where I think when Matt and I started this, looking at portfolios that could reach 20 or 30% renewable in the course of a year. That was considered the frontier. And we never thought you could go over 50% instantaneous. And now that really has shown there's really no ceiling to how far we can go. The technology has really progressed, the inverter capability and the battery storage being the key enabler to that.
Thanks.
Someone had their hand up in here.
Was a uniform renewable resource assumed for the solar and the wind, or did you use any geographic diversity across the rail belt, seeing how it's so wide?
Yeah, we used geographic diversity. So we use the Global Wind Atlas to identify areas, and then the ERA 5 satellite data and some calibration. Yeah.
Felicia, can you describe how this study compares with the other studies that are going on, NREL, et cetera? How does this compare or fit in with the utility work as well as other entities?
So I think I can really only speak to the NREL study that I'm most familiar with. NREL study, I think, is very complementary to this work. They looked at those year-to-year transitions of what you want to build when, at what time. Whereas we did not look at that. We only looked at 2050. I think they have some very good information on that. NREL, however, did not do the transmission analysis study portion, which involved the power system modeling side where we looked at stability. And due to that, there are costs associated with stability that aren't included in their costs. And those are the two major differences. Where we aligned assumptions where it made sense to, and we have been in contact with each other. And I think I'll only speak to the NREL one I know most about.
And a question from online, were any potential pumped storage projects included?
We did evaluate pumped storage. And there's a paper we put out last year about different locations and what would the cost of those be for different locations in the Railbelt. However, it was significantly more costly than battery energy storage at the time that we looked into it. So therefore, we've really only pursued battery energy storage in our portfolio.
Another online question. Have you factored in a way to replace the heat that the Fairbanks combined heat and power plants, the four, Aurora, UAF, Eielson, and Wainwright provide in the winter?
So we did not make any assumptions on the independent power producers such as Aurora and UAF. We assumed they are in place in all of our scenarios. However, this brings up a very important point that we did not look into decarbonization of the heating sector, or if you were, we did not look into retiring those planes, but if we were to do that, how would you make up for that heat? We didn't look into those things.
Person?
Hi, well, thank you very much for your work. Very, very impressive, the amount of work that was done, and very interesting results. I guess, and this was brought up as a bullet point at the end there, you know, I'm kind of interested in some lower cost renewable scenarios. It looks like the hydro, the tidal, and the nuclear, at least on the capital side, was what was driving up the cost of the renewable scenarios. And so just wondering if you thought about doing a pure wind and solar without hydro, nuclear, and tidal. I know that wouldn't get you to the level of decarbonization because of the curtailment issue. You'd probably be something much closer to the NREL results, which, you know, showed that costs were minimized at about 78% renewable penetration, leaving, you know, 22% natural gas. So just curious what your thoughts are on that kind of a scenario.
Yeah. Basically, our limited resources eventually made us not do that scenario, but we're definitely considering it. We just weren't able to quite make that one happen. But yeah, so and that is definitely something that we'd consider doing.
Several questions on timing. To what extent are the economic and might the economic analysis be affected by the speed of transition, or did you consider time-bound pathways to get there, or the timing of change? What happens first in all of these scenarios?
In short, no. Yeah, so we did not do a year by year kind of capacity expansion study. And that is kind of, yeah, that's something that would be an option for a future study.
Question for Steve, how are we
think
going to pay for all this?
Sorry, just real quick on the timing issue. I think there is something, while we didn't look at the year-to-year transition, I think in terms of timing, there is an opportunity now for really anywhere, but specifically as well for the Alaska Railbelt. There are now federal incentives in place with the Inflation Reduction Act. So that was assumed that to have the investment tax credits. So that is an opportunity available between 30 and 50%, 30, 40% of the capital of all of these systems going in place to get a tax credit from the federal government. And so that is not necessarily time sensitive, but certainly in the closer portion of the time horizon than 2050. So the next 5-10 years, a key thing to consider.
Steve, how are we going to pay for all this?
Well, I tried to touch on that in my slide deck, but it's worth reiterating that the I think the way to think about it is that we're not already paying for it, but if we were to take a BAU type approach with minimal capital investment, we would end up with an extremely high fuel bill. And I don't have the numbers in front of me, but they're actually in the notes to the slides and it can be found on the tables. It's a remarkably even trade-off of fuel under the BAU in 2050, about $750 million per year would projected to be spent on fuel, more or less, well, I shouldn't say headed out of state, depending on who's supplying it, but versus something like $600 to $700 million per year spent on paying off the capital. So that was a little bit of another surprise to me. It sort of looks like a 1-for-1 shift from fuel to capital, as opposed to a big change in the overall magnitude. So how are we going to pay for this? We're going to pay for this with savings on fuel.
And you touched on the answer to a question that came in while you were speaking, which is, did you look at the amount of money that stays in state under each of the scenarios? And I heard you just say that for fuel, most of it's going out of state.
Well, the devil is in the details on
Yeah.
that one, but it does make me want to say that it seems to me like we have a huge opportunity to do something that economists used to be jumping up and down every day about in Alaska, which was import substitution. Does anybody remember that? Got one or two nods. This seems like reinventing our Railbelt energy grid to be low carbon would be essentially the ultimate import substitution project that Alaska could undertake.
I know that the oil and gas industry has been having a lot of economic favors given to them by the government. And there's not been the cost of the environmental impact over the many decades that we've had oil and gas spiraling up. And is that something that you guys have put into this thought too? Is that we've got this cost, if we go more for fuel, the environmental impact that's going to have, our share of that, of the world?
I've got the mic, so I'm going to answer first. There's a short version of the answer, which is we received some early, not really feedback, but early, very helpful suggestions. I'm looking at you, David Lockhart, that maybe we should explicitly consider a carbon tax as part of our scenarios or a part of our sensitivity cases. And we did not do that. But of course, one could, and that would be a fairly let's say, straightforward way to to put that whole constellation of concerns into the analysis. So I guess what I wanted to make clear is that although we are well aware that a carbon tax or a carbon fee, I should say, that a carbon fee might change a lot of these cost results, we chose to not do it as an explicit sensitivity.
I'll just say one more thing on that, is that there are other associated costs associated with basically not decarbonizing that others could study and include. And hopefully the information we provided here could aid that type of study. Just for example, the air pollution problem in Fairbanks does have direct cost consequences that are not captured in the study.
There's a question on the status and proposals for Cook Inlet Tidal. Where can somebody find more information out about that?
There is a Cook Inlet working group, and they can reach out to us and I can point them in the right direction.
Question.
Yes, thank you very much for that. That was pretty comprehensive and great overview of a lot of things that have to do with load and cost of service and everything in between. My question, this is Steve Conkle, is basically this is a transmission question or generation and transmission. With the $206 million that's been proposed for the Railbelt grid and integration, what's the basic approach towards that in terms of what you described? Are there grid forming inverters or options to use the latest technology, or this is just a step in the investment in the transmission? And how important is it, given the fact that some people would rather not invest anything in capital except have an alternative, at least because of the Inflation Reduction Act, it makes it extremely attractive to have that money matched by the federal government. And then my second question has to do with the timing of decision making. And that's one example of something that's right before us right now. But how do you see these decisions being made over the next several years or so to get to a place where we have consensus on at least the scenario type approach, or how critical it is to make decisions in the next 10 years?
Yeah. Please.
I guess on the first one, the near-term investments, while we didn't evaluate those specific GRIP projects, I think it's clear that all of the portfolios we did look at had components of that included. So all of them included the transmission additions between the north and central and Kenai. And I had the one chart that showed the flows, the hourly flows across the transmission system, and all of them had a big increase. So that certainly a key enabler to any of those scenarios is going to be ability to transfer power across the rail belt much more than it is today. The other component of that is, battery storage investments, and those can be done today to, of course, all of those portfolios we looked at had sizable increases in the amount of battery storage on the system. So certainly, again, an enabler. We didn't look at if that's the near-term cost benefit analysis of that, but to your point around the timing of the change, there is significant federal funding, both in the GRIP funding, but also in the investment tax credits and tax credits from the federal level to help support that. And certainly around the battery storage that could go into place for those projects, the grid forming capability that Matt talked about, that is commercially available today and could be implemented as well. Yeah.
Well, I was just trying to remind myself how exactly we treated the HVDC GRIP line. The HVDC line is in all four scenarios as a resource. I'm hoping, if I need to be corrected, correct me. I think it's in all four. I think it's in the BAU also. And I'm pretty confident, fingers crossed, that the states or the non-federal, 50% of that cost got bundled into all the costs that we were just looking at on the screen. At least that was the intent. But the resource is basically assumed to be a done deal, the part that's been already funded. And that also includes some batteries, which are in all 4 scenarios, including the BAU.
Question about grid forming inverters. Is there any Alaska experience with grid forming inverters that we can draw upon?
Yeah, I mean, Alaska has been, I mean, AVEC, our rural Alaska has been doing grid forming inverters for over a decade now. And so, it's emerging, but it's also been around for a while. And I think maybe what's more new is using them at this scale and on a large system like this, but on smaller systems, they've been really enabling large penetrations of renewables for quite a while now.
So should we let AVEC run the Railbelt?
No, Bill?
Oh, a question back there first.
Hey, great work. Awesome. Thanks, guys. Can you remind all of us the large islanded grids of the world that are leading, what percentage renewables are they at, both in average and in peak?
Ooh, off the top of my head, large island grids of the world. Yeah, Texas is a big electrical island. What are they at? Not a good example. I don't know, 30% annual average, but approaching 75-80% instantaneous. I think Ireland is another big island.
70%, yes.
Yep.
Ireland, Texas, parts of Australia, the southern province of Australia.
Iceland.
Sorry. The real actual large system operation is around 70% instantaneous. So at any moment, 70% of that power would be from renewables. And that's not just like, taking a state, like just saying California, it's the whole system, the whole interconnection is actually doing it. There's parts so the southern province, South Australia, and Australia is up around that region as well. And then when you look at smaller systems, so for instance, Kauai, which is maybe 1/10 the size of the Railbelt, they have done 100% renewables. It's not all inverter based, but it is 100. They have operated for periods of time at 100%. So they're definitely pushing. And of course, these big systems, they're very careful. They're not exactly pushing the envelope. That's where they're actually comfortable putting the system today.
We had a chat come in saying Iceland ought to be added to the list as well.
Iceland is a little different in that a lot of hydro, a lot of geothermal. So again, going back to the synchronous machine capability, interacts with the grid a little differently. But yes, they are at 100% renewable.
First, thanks. Great presentation. What a fun study. My question is, and from the nuclear side of things, somebody mentioned 2 medium-sized nukes. I'm really curious what you consider a medium-sized nuke, and what did you use as a cost basis? What kind of capital did you use for nukes?
So we use small modular reactors, SMR technology. So we assume that was the technology that we use. And so what size? It was like 200 something or 300 something megawatts. What? Yeah, 200 in the northern and 300 something in central. And what cost did we assume?
We actually end up taking costs from NREL's technology baseline and increasing them for Alaska high cost by, I think, 25%. That was the multiplier on, and then giving them credit for a 30% ITC. And the resulting number was something like, it's in the tables, but it's something like $8,500 per kilowatt was what went into the tallying up the cost.
And that a similar process was used for all technologies. MRELs.
Just curious, curious considering there's been no SMRs built to date.
Right, that's the point where cost projections are highly uncertain, especially for tidal and nuclear, where you don't really, SMRs and tidal don't really exist, at least on that scale today.
Question on the stability analysis. What were the assumptions for spinning reserves?
Yeah, I mean, on the spinning reserve, so this is embedded in the generation analysis, follows basically today's operating practices, and the loss of the largest unit is setting the spinning reserve requirement. I'd have to go back and look at exactly the details of that. And there's a reserve sharing agreement and how that gets shared across the Railbelt system. So we follow the same rules applied to that. So at any given time, the loss of the largest generator is going to be covered by spinning reserve. The spinning reserve means basically today generation that can ramp up very quickly. So it's going to be online generation that can increase its output. In these future portfolios that can be provided by that same generation, as well as battery storage that can quickly discharge to make up for that.
I was at a meeting at Chugach Electric a little over a week ago and heard from some engineers about a 20+ year timeline to implement and integrate renewables. And I kind of I'm wondering how your scenarios, I think you might have built that in, that it's going to take a while to implement things along the way and the sequencing of that. So I'm kind of wondering about these island grids that you've talked about. How long have these states or countries been fiddling with this versus where we are now? We're kind of, are we at ground zero, Alaska?
Ground zero. I don't know if I'd call it ground zero. I guess, set the context to begin with. We looked at these very high decarbonization scenarios that we're looking at 80, 90% plus, and that is going to be a transition. I think near term, though, there's opportunities to relatively quickly integrate early tranches of wind and solar resources. So the challenges, certainly when we talk about stability and some of the amount of battery storage that's needed, that's really needed at these very high penetration levels to push the envelope further. Early additions, kind of the next wind plant, the next solar plant, I think that's to some extent the low-hanging fruit. Still a lot of engineering that needs to go into that, especially for a system like the Railbelt. But I think we're not on decades-long time frame to get the next additions of those renewables in. I think that can be deployed quicker. Yeah, I'd say, like, for the Hawaii example, it's been a transition over the last 10 to 15 years. It started off with some pretty large wind installations there about 10, 15 years ago, that was successful across the islands. Then after that, it was rooftop solar, quickly grew. At this point, rooftop solar collectively is the largest share of energy on each of the islands. And just recently, I would say over the past 3 to 4 years, it's been a rapid deployment of solar and storage resources. So as soon as the cost of battery storage came down and solar, that is now more economic than oil-fired generation there, and it picked up very quickly. So a series of projects have come in over the last 2 years that have really started taking those islands from 30% annual renewables up to 50 to 60 by the end of this year, probably. So
maybe I just add on to that. Yeah, they've been going 10 to 15 years. And I think Alaska has the benefit of the lessons learned from all of that experience. It's not that this thing is gate kept at you can't go faster than 10 or 15 years. Those people that have been doing it and where they are now, they were the first runners. They weren't sure what they would do. And you will look and see, for instance, Ireland, about 5 or 6 times the Railbelt, but very wind rich now, running at 70%, right? If only a few years ago, they set their limit at 50%. They wouldn't go more than 50% wind plus their HVDC link. Then they moved it to 55, 60, and it's a steady increment as they get more comfortable with the technology, the response, and operating the system in that way, developing new markets to procure the services that they need for that. They keep on moving the bar. And I think that's, a reasonable and good way to do it, in the sense that you need to understand where you are and where you're comfortable with your own experience, and not push too far. But when you get that, you're able to keep moving the bar and keep on and keep pressing forward with the evolution of the grid, and do that at a rate that makes sense with what lessons you can take from others and where you are comfortable with your own operational experience.
We're gonna have to.
We'll do one more question,
One more.
and then we'll do the polling. It's one question, takes a couple minutes.
And so while you're getting those questions, while you're getting that question, any of the questions that were entered online that we didn't get to, we'll record those and try to get answers to the people who put them. Thanks.
Sorry, one more. For the business as usual, Steve, remind me, did that contemplate LNG? Did it include the capital infrastructure? Did it include the benefit of storage? Did it include geopolitical volatility, or was it just $14 flat? Sorry, 3 questions at once. We're awful.
I think the short answer, and Jeremy can fill in the gaps, is we assumed $14 gas, and that's sort of like the all-in cost. Like, we can get as much $14 gas as we want in the BAU. Is that fair to say?
Inclusive of the term belt. Yeah.
Well, I think the assumption is somebody would step up to supply it in the same way that, let's say, NSTAR supplies gas, and the somebody would take on the responsibility of the gas infrastructure and deliver to the Railbelt at 14.
Are you talking about gas storage? Yeah, so we did not place any restrictions on the use of gas in terms of like flexibility, in terms of ramp rates and stuff. So that means, so today's system, there are restrictions. And so that means that what we assumed that somehow basically the system in 2050 would need to be more flexible than the system that exists today. And we did not explicitly model how that would happen. We just made that assumption. And, we got some feedback. There's a lot of uncertainties about what an LNG import system would necessarily look like and what flexibility would come with that. And so we didn't really go down that route, but that is an assumption that was made.
Awesome. Thank you so much. So this is just the beginning, right, for this study. So this is phase 1. All of these folks have been working on it for like 2 years. And so the next question is like, what's next, right? And there's a bunch of directions to take it. But these folks would like to know what you all would like to know next for the next phase. And so we're going to pull up a poll. And so if you pull out your phones, there's a QR code and then also a little and some numbers that you can put in. And we're basically going to ask you to rank what are your priorities for phase 2? What are the priorities for what next should be studied? You should be able to rank 3 of them. If you click on it and want to change your answer, just unclick it and pick a new one. It'll gray it out when you've had all your votes. Lisa, can we go back to the other one with a larger QR code, please? Sorry, I thought it was a simple switch. Thanks. Excellent. Appreciate it. All right, someone let me know if that works. All right, people still working on it. But a couple more minutes. Excellent. Thank you all so much. Next steps for this is that we will send out this recording. We'll send out this full slide deck, the answers to this poll to all of your email addresses. If you're either already on the email serve that's been hearing about this, great. We'll send that out to you. If you want to be included on it, please put your name over here. We'll be in touch with next steps and what came to fruition from this conversation. And we appreciate y'all coming out. Thank you so much. The researchers are going to be here for a little bit longer, and so you can come ask some more questions. And we just have to be out of here at 9. Grab some food before you leave. And thank you so much.